In this PowerPoint, we're going to look at a topic called locating roots. Have a go at the start question, press pause on the PowerPoint and have a go. On the next slide, I'll go through the answers. I'm now going to go through the answers to the starter question. It says that the diagram shows the graph of f of x equals x cubed plus 2x squared minus 4x minus 5. And question 8 asks, how many roots exist for f of x equals 0? When we refer to the roots of an equation, we're always looking at where does that equation equal 0. On a graph, this means where does the graph meet the x-axis. We can see that in this cubic graph, the graph meets the x-axis in 3 different places. So this cubic has 3 roots. Question B asks, how many roots of f of x equals 0 lie between 0 and 3? Well, on our picture, if we look at the scale, 3 would be here. Between 0 and 3, the graph goes through the x-axis just once. So one of those roots lies between 0 and 3. Question C asks, how could you prove without the diagram that there was only one root between 1 and 2? This is a question that we'll answer as we go through the PowerPoint. By the end of the PowerPoint, you should be able to locate the roots of a function f of x and know how to verify that a root is correct given to a certain number of decimal places. This example asks us to show that the function has a root between 1 and 2. Now we can see on the picture that there is a root between 1 and 2. This means if we find 1 on the x-axis and then 2 on the x-axis, we can see that the function goes through the x-axis somewhere between 1 and 2. But to prove this mathematically, we could substitute the numbers 1 and 2 into the function. First of all, if we substitute the number 1 into the function, we get an answer of minus 6. This means that when x is 1, the y-coordinate is minus 6. We could then substitute 2 into the function. This gives an answer of 3. So when x is 2, the y-coordinate is 3, which is a positive number. So one of our y-coordinates was negative, our other y-coordinate was positive. For the y-coordinate to change from a negative number to a positive number, the graph must have travelled through the x-axis. We say that there's a change of sign. One positive and one negative means there's a change of sign. Therefore, there must have been a root between 1 and 2. In other words, the graph went through the x-axis between 1 and 2. The diagram shows a sketch of Here's a question for you to have a go at. Press pause and have a go. On the next slide, I'll go through the answer. Hopefully by now you've had a go at the question. This is asking, is there a root between 0.5 and 1.5? So what you've probably done is substituted 0.5 into the function, and this gives an answer of minus 11 over 8, and the negative part is useful. Then hopefully you substituted 1.5 into the function and also got a negative answer. At this stage, you may have decided that because there was no change of sign, that there would be no root. However, this is a bit of a trick question, and if you've come to that conclusion, unfortunately, you're not correct. Let me show you a picture of this cubic graph. We were trying to identify whether there were any roots between 0.5 and 1.5. If we have a look at where 0.5 and 1.5 are on the graph, we can actually see that there are 2 roots between 0.5 and 1.5. When we put 0.5 into the function, we got a negative y-coordinate, and when you put 1.5 into the function, you also got a negative y-coordinate. But that doesn't mean that the graph did not hit or go through the x-axis. This one did in fact go up through the x-axis, but then turned and came back down through the x-axis, back into the negative y region. So this graph actually had two roots in that interval. So what we need to talk about next is, when does this change of sign rule work? When is it okay to say that if there's no change of sign, there are no roots, and if there is a change of sign, there is a root? When does that work and when does it not? Let's investigate a little further. The graph needs to be increasing or decreasing in the interval to show that there is exactly one root between 2 points. So for example, if we look at this cubic graph and we just look between 1 and 2, so 1 there and 2 there, between 1 and 2 we can see that the graph is constantly increasing. It doesn't turn, it's always going in the same direction. So if we substituted 1 and 2 into the function, and one gave a positive answer and the other gave a negative, then it would be perfectly correct to say that a change of sign means that there is exactly one root. Now let's look at this graph again, and we'll look at the interval between 0.5 and 1.5. So 0.5 is here, 1.5 is here. So now we're looking at this part of the graph, coloured in yellow. This part of the graph is not always increasing or always decreasing. Some parts of the yellow section are going upwards, other parts are going downwards. It changes direction. So when we substitute f of 0.5 and f of 1.5, even though they both gave negative answers, that doesn't mean that there were no solutions. It must mean that there are an even number of solutions. Maybe it didn't go through the x-axis, or maybe it went through twice, like we can see in this picture, or it could have even gone through 4, 6, 8, or 10 times, any even number. So it's gone through that x-axis, but then come back down and gone through the x-axis again. So if your graph is not increasing or decreasing on the interval, then the change of sign rule does not work. Here's some more information that you'll find in your booklet. There are 3 situations which you need to watch out for when using the change of sign rule to locate roots. A change of sign does not necessarily mean that there's exactly one root. It could mean that there's exactly one root, but not necessarily. There will be one root if the graph is strictly increasing or strictly decreasing. But here are 3 situations that you need to watch out for. In the picture on the left-hand side, there are multiple roots within the interval a, b. We can see that at a, there's a positive y coordinate, and at b, there's a negative y coordinate. So if you found f of a and f of b, you would see a change of sign. However, that doesn't mean that there's exactly one root. In fact, it could be any odd number of roots. We can see in this case there were actually 3. The middle picture shows a graph where between a and b there are 2 roots. F of a would be a negative value, f of b would also be a negative value. But to say that there's no change of sign means there are no roots would be a lie. We can see that there are 2 roots. The reason is that this graph is not strictly increasing or decreasing between A and B. It turns and changes direction. So if you do not have a change of sign, that doesn't necessarily mean there are no roots. It actually means there could be any even number of roots, like 0, 2, 4, 6, etc. The third picture on the right-hand side shows a different situation where a change of sign doesn't necessarily mean that there's exactly one root. Here we can see that at A, we have a positive y coordinate, so f of A will be positive. B gives a negative y coordinate, f of B is negative. However, that doesn't mean that there's exactly one root. We can see here that between A and B, this graph never goes through the x-axis. This graph's actually got an asymptote. So the graph does not go through the x-axis. There are 0 roots, even though there's a change of sign. In this example, we have a cubic function, and we're told that it has a root at x equals 1.382. That means if we put the function equal to 0 and solve it, one of the answers will be 1.382. It also means that the cubic graph goes through the x-axis at 1.382. We are asked to verify that this root is correct to 3 decimal places, which means that this isn't the exact answer, this is a rounded version. And we are trying to show that to 3 decimal places, this would be correct. The way to verify this is linked to upper and lower bounds that you would have seen at GCSE. If we take a measurement like 1.382 and we write down its upper and lower bound, the upper bound would be 1.3825 and the lower bound would be 1.3815. Any values between the upper and lower bound would round to 1.382. So what we need to show in order to verify that this answer is correct to 3 decimal places is that when we find f of 1.3825 and f of 1.3815, we should hopefully see a change of sign. So let's work out f of 1.3825 and f of 1.3815. So onto our calculator, we would type in the cubic and insert those numbers. The first one gives an answer of minus 4.57 times 10 to the minus 4. The second gives an answer of 3.98 times 10 to the power of minus 4. So we can see that one is negative and the other is positive. There is a change of sign, therefore 1.382 was correct to 3 decimal places.